Good morning. I wanted to thank the organizers for giving me this chance to talk about spatial encoding and K-space. This is actually my very favorite lecture when we're teaching MRI, because this is where we make that big leap from, physics in a test tube to really mapping things and making an image. No conflicts. So here's what I'll talk about today. I'm going to start with a pretty brief overview of the basics of gradient encoding. And then what I'm going to spend a lot of the lecture on is a focus on K-space. And I know this is physics for physicists, and you all know K-space. But I personally really like to think in terms of pictures and videos and maybe cartoons. And in my experience, even a lot of very smart graduate students and postdocs are still a little bit unclear on exactly what connects our physical experiment to the K-space and then to the reconstruction. So I'm going to try and present it in a more pictorial way, and hopefully you find some value in that. And then once we have that established, we'll go into some more advanced topics like Nyquist relations and beyond non-Fourier encoding. Okay, so let's start with gradients, as you're hopefully familiar with. So gradients are just spatial variations in the BZ field. They add and subtract to the main field, and so they also add and subtract to the Larmor frequency. So of course we begin with, this is how I'll show, let's say, the z equals 0 plane, and there's a uniform magnetic field everywhere, a uniform Larmor frequency, say 3 Tesla. And then when we turn on a gradient, there's a little bit of variation, maybe from 2.96 to 3.04 Tesla or something like that along some direction. In MRI, typically when we say gradient, that is synonymous with linear gradient, and that's just to say that the offset from 3 Tesla or from the Larmor frequency is directly proportional to some coordinate, x or y. But of course, we don't usually talk about the 3 Tesla. We're in the rotating frame, so we usually just focus on, I'll sort of interchangeably say frequency for offset when I really mean offset frequency. And I'll also be showing gradients with this kind of notation, just focusing on the offset. Okay, so the first thing we can do with gradients for spatial localization is we can excite just one physical plane of our sample. So we start with our spins all on resonance. They're at the Larmor frequency. And if we turn on a z gradient, we've essentially created this situation. So now if we send in some monochromatic RF, which is essentially what a shaped pulse is, we're going to only excite those spins that are on resonance with the light that we're sending in. So we're only going to excite spins in that plane. So now if we later go ahead and turn the gradient off, everything is back on resonance, back at the Larmor frequency, but the only spins in the plane and that are detectable are these in this plane of our object or brain. Okay, so now that we know we're only dealing with one plane of signal, we can talk about encoding spins within the plane. So for example, we can turn on an X gradient, and then so spins at this position might give off this signal here, and then at this green position, there are more spins in this column, so that's a bigger signal, and fewer spins in this column, and that's a smaller signal. But of course, we don't detect those signals individually. We're always detecting the bulk magnetization, so that's going to be the simultaneous sum of all of these together, and that's what comes out to be an echo. If we Fourier transform this, we're going to get the frequency content of this signal, and then what that gives us back is essentially a density projection onto the x-axis. We can also turn on gradients in the y direction, and this works just the same way. And now we have, let's say, the red component of our signal looks like this, and so on and so forth. Just like before, we're not detecting these individually. We detect the sum. And once again, if we Fourier transform it, that gives us the frequency content of that echo we acquired, which is now a projection of the object onto the y-axis. So that's a great interpretation if you have a whole echo acquired under a constant field. But it's really only a great interpretation if you have a whole echo acquired under a constant field. For example, what if the field changes with the readout? Then this starts to fall apart. If you want to know what the significance is of adding or subtracting a single point from your echo, it's not so clear. And also non-Fourier encodings are hard to understand this way. So how do we understand them? Of course, the answer is that our data, our MRI data, are actually points in k-space. Everybody knows this. And these are the equations that show that. So this is, we say our signal as a function of time is this. And with a small rearrangement of variable, we can recognize that as a Fourier transform of our object and our spin density. And therefore, if you inverse Fourier transform the signal you acquire, you can get the object back. But as I said, I want to attempt a more sort of pictorial explanation of this. So we're going to start with, bear with me, the Fruitier transform. So imagine you start with a smoothie. A smoothie is a very simple thing. But if someone hands you a smoothie, it's very hard to know actually what ingredients are in it. So we can think of this transform as a process that given a smoothie, you can solve for the recipe of that smoothie. And the process is this. So you take this smoothie and you dot it with a fruit, this is a normalized fruit. So you multiply them and then sum it up or weigh the whole thing. You get this number. And this number tells you how much of that fruit was in the original smoothie. So you repeat this process for every possible fruit, and eventually you can say, okay, now I definitely know the recipe, and you can call that recipe the coefficients of this decomposition. Taking it a step further, you can take those coefficients and you can plot them on some kind of axis. And now you can step back from the whole process and say, okay, this thing on the right that I solved for is the transform of my mystery smoothie. So we also use transform as the noun, as the recipe that you come out with. So that may seem sort of a nonsense example, but really the Fourier transform is very much the same thing. So we start with some mystery function, and we know that it actually is composed of a bunch of sine waves, or can be composed from a bunch of sine waves. And the way that we solve for that recipe is we multiply our mystery function with these ingredient functions, this basis. And this is not just a regular multiplication, it's an inner product. So we're multiplying and then summing over all space to get a number. And that number is going to tell us how much of this ingredient function was hiding in the mystery function. So just like with the smoothies, we can do this for all the mystery functions for the entire basis. And we get these coefficients, and we can go ahead and plot them along some axis. And then we can step back and say, okay, this thing on the right is the Fourier transform of this mystery function that we started with. So just to start connecting this a little bit more with MRI, our mystery in MRI is typically the function in X space, or the object. And these coefficients are coefficients in K space, which is our data. Okay, so that's 1D K space. Now let's take a closer look at 2D K space, but it's really the same thing. So when you look at K space, every single number in here is just a coefficient on some ingredient function. So for example, this number here tells me how much of this, I'm pointing to the point 4, 0, and that tells me how much of this mystery function was hiding in my object. And it's 4, 0 because it has 4 oscillations along X and none along Y. And then this coefficient here tells me how much of this function was in my object, and that's 32 oscillations along X, none along Y. There are also functions that have oscillations along Y and not X, like this one. And other functions, I hope that shows up a little bit better on the big screen, but some of them have oscillations in both directions. So like this ingredient function, basis function, has 32 oscillations in every row and 32 oscillations in every column. So if we take this recipe here, essentially, and add up all of these functions with the prescribed coefficients, we're going to get back our image. So that is the same as the inverse Fourier transform. Okay, so that's K-space. That's sort of how we get the numbers that go into K-space, and also how we use K-space. But I still haven't connected this at all to the MR experiment. So let's start making an attempt there. So what I'm showing here is a 9 by 9 array of spins in, let's say the z equals 0 plane. And right now they're on resonance. That's what this green bar represents. And we're in the rotating frame, so they're just standing still. So at this time, we could go ahead and plot what mx is at every location. And it's just 1, which is not very interesting. And my is 0 everywhere. But now let's go ahead and turn on a gradient. So what you see is that these spins that are still on the Larmor frequency at the green frequency, they're still stationary. But the blue spins are moving at a higher frequency, so they're developing a lead. And these spins over here are moving at a lower frequency, so they're developing a lag. And so now you start getting spins pointing in all these different directions, and it starts looking quite complicated. However, if we freeze time or turn off the gradient, either or, we can go ahead and try and make some sense of it. So if you imagine just plotting what the x component of this signal is across the field of view, or of this magnetization across the field of view. So it's 1 in this column and -1 in these columns. It's 0 here. And then here's an actual, just a literal plot of each one. And we start realizing that it's starting to look like a cosine function. And if we do the same for my, so it's my is 0 here and -1 and +1, it's looking like a sine function. And this is especially true because we don't have 9 by 9 spins. We have, a mole of spins or a millimole of spins. So this really does become a continuous function across space, and it does approach a cosine and a sine wave. And specifically what we've got here is actually one of the basis functions from our Fourier series, from our 2D Fourier series, the kx equals 1. Okay, so we can repeat this for, now let's take on, I guess, like a whole readout, for example. So we're going to start again with all the spins. We're in the rotating frame, and they're all pointing in one direction. And actually, before we even start evolving under the gradient, we see that this is already a Fourier basis function. This is the kx equals 0 function. So we associate it with that location in k-space. Now, if we let time happen and let them evolve under the gradient, the spins do this. And this is just what we saw in the previous slide. And this is the kx equals 1 function. If we let time, and we associate that with this location in k-space. If we let time keep running, they keep winding up. Again, each one is just evolving at its own frequency. And this might look a bit complicated, but if we look at the continuous case, it's easy to see that this is the kx equals 2 basis function. We associate it with that location. Do just a couple more here. Keep going, and actually this one is associated with the kx equals 3 function, associated with that location in k-space. And now we're at kx equals 4. So the point of this is essentially that this is showing why gradients actually wind spins into Fourier basis functions. This is why gradients move us through k-space, and essentially the amount of winding accumulates from the gradient being on over a period of time. But I still haven't actually talked about our data. This is only an abstract plane of uniform density spins. How exactly does it relate to what you measure at the MR scanner? So let's take that on next. So this is the same kind of cartoon, but now we're talking about a real object. And what's important is that now, in some locations, basically the magnitude depends on location. So in some locations, the magnitude is 0. And even where it's not 0, if you pay attention, you can see that some places have a lot of spins and some places have very few spins. But the evolution, when you turn on a gradient, is still the same. Each one is just evolving at its local frequency, and you're winding up these spins. And if you can keep an eye on the right, it's sort of like you're superimposing onto this object those same Fourier functions. So you can kind of see through it the k equals 1 function, the k equals 2 function, so on and so forth. So let's freeze time at one of those moments, and you've got your object magnetization wound up by a gradient. Well, what this is equal to mathematically is the product of your object density, which assumes no winding, and some idealized basis function that has unit magnitude at all the locations. But we go one step further because we don't detect our object magnetization per se. We detect the net magnetization from this wound up object. So that's like integrating overall space. And then what you'd have to do on the right to represent this integral is take an inner product of our mystery object and this idealized basis function. So this is what kind of connects back to what we were saying, where if you take a mystery function and multiply it by the basis function and integrate overall space, you take that direct product, the number that you get is the coefficient or the recipe. And that is why what we measure in the MR scanner, even though it's the net magnetization of this wound object, it really is a Fourier coefficient. So just to bring this sort of full circle back to the equations that are probably more familiar to you, what we're measuring physically is this wound up object. But mathematically, that's equivalent to the inner product of our unmodulated spin density, our unmodulated mystery object, and these basis functions. And that's why we're getting out those Fourier coefficients. Okay, so we've talked about K-space, both how the experiment gives us K-space, and then how we take K-space data and turn it back into an image. Now all we have to do is collect K-space, right? So we'll talk about that next. And there are many, many ways to sample K-space, to traverse K-space as we acquire it. Both typically if we acquire it, anything you acquire in a straight line is considered frequency encoding, and discontinuous points in K-space that are acquired over different TRs is sort of like a kind of phase encoding. But this meeting is a great showcase of all the different ways that people actually acquire K-space. But they all share one thing in common, which is that they need to acquire enough K-space. So we're going to talk a little bit about what that means. And of course, there are Nyquist relationships that tell you how much K-space you need to acquire. So the sampling between K-space points is related to the field of view. So this might be okay sampling for a small field of view, but if you want a larger field of view, you need to sample more densely. And also relations between the extent of sampling in K-space and the resolution. So for a low-res acquisition, maybe you just have to go out this far in K-space, but for higher res, you'll need to go further out in K-space. But what I wanted to convey today is that really these all boil down to one thing, which is the encoding functions need to uniquely encode each location. So let's try and make that a little bit more tangible. So one thing to make them unique is you need the phase change for each position to be unique. So if we go back to our friendly 9x9 array of spins, we let them evolve under the gradient. Let's say we acquired the k equals 0, and we try to acquire the next point here. Now, if you look across the row, the phase change is unique to each position, so that's good. But if we'd have waited a little bit longer, and let's say stopped here, now if you look, this position and this position appear to have exactly the same phase change. And if you think about it, you're going to have that problem anytime you rotate more than pi, because essentially this spin that went pi plus a little bit is going to have exactly the same signal as a spin that went in the opposite direction by a complementary amount. However, we can also think of that as a problem of field of view, because if we knew that our field of view, that spins only existed in this part of the field of view, that sampling would be fine, because now we've eliminated the redundancy by sort of cutting off the encoding functions. Okay, so that's the general idea or the motivation behind this sampling requirement. Let's see if we can turn it into an equation. So we want the phase change of the fastest spin to be less than pi. So if you're talking about linear gradients, it's easy enough to express this phase change as a function of your x sampling, kx sampling, and your field of view, and then you can get this handy equation. But the more general truth for any kind of encoding is really this one. So we can do a similar analysis for the Nyquist relation of related to resolution. So let's say you want to resolve the septum in my daughter's nose here, which you can't really see. If you're using an encoding function like this, clearly it's going to average together the spins in her nostrils and her septum. And so you're not going to be able to resolve them. If you use a finer encoding function like this one, you can start to see sort of some structure in there, but you really can't resolve it. But just around the time that, oh, it's hard to see, but this is the peak to trough distance starts becoming very comparable to this septum, you can really resolve it quite clearly. And here's just a high resolution version for cuteness. So our sampling requirement in the broadest sense is just that the encoding function needs to distinguish neighbors. And one way to guarantee that is that the peak to trough distance should be smaller than the smallest feature. Again, for linear gradients, you can easily write this in terms of k max, and smallest feature we associate it with our voxel size, and then you come out with an equation like this. But more generally, this is the reasoning behind it. Okay, so for my last few minutes, I want to talk about a topic near and dear to my heart, which is non-Fourier encoding or post-Fourier encoding. So can we represent these in k-space? All right, I've been talking about how your signal is basically related to this inner product between your object and an encoding function. So for example, the spins in your brain and some Fourier function. It is also true, just by a change of basis, that you can make the same statement for both of them in the Fourier transform domain. So now we are saying that our signal is basically equivalent to an inner product of the object's k-space, and the Fourier transform of this is like a bunch of zeros and 1, 1. So what this is telling us is that our signal is picking out one point in k-space, which is good. We already knew that. But what's interesting is that this second interpretation is not limited to Fourier encodings. This is true for any encoding, for coil weighting, if you have nonlinear gradient windings, if you have RF putting in some crazy phase, oops, that's all true. So you can really think of the Fourier transform of whatever your encoding function is as a sampling function in k-space quite broadly. But what's different is that now your data, if your sampling function is not a simple 1 in a sea of zeros, your data is not just one point in k-space, it's a weighted average of k-space points. So let me show you what I mean by that. So for example, here I'm showing standard Fourier linear gradient encoding. The top here is real space, so x and y, and on the bottom I'm showing the Fourier transform of that in k-space. So in this case, as we said, our measurement is a single point. And also, as we change kx and ky, it's going to translate that sampling function across k-space. So as we expect, so our sampling function goes all around k-space, and we are collecting data all the time, and eventually we've collected all of k-space. Now consider we have, in addition to the linear gradients, we have some coil sensitivity weighting. So maybe these are the hotspots in the coil sensitivities. So now the Fourier transform of these is this thing, and our measurement is a weighted average. However, just like before, kx and ky are going to translate the sampling function across k-space, so we're taking these measurements everywhere. And this is not like some arcane physics detail. This is actually really important because the fact that these sampling functions have measurement outside of our regular trajectory is actually why parallel imaging works. The fact that we're sampling the wings off of the nominal gradient trajectory is especially why grappa works, or grappa is most closely associated with that point of view. Okay, so now we can take it one step further. We can consider linear gradient encoding, coil weighting from the RF, and also we're going to bring in some dynamic nonlinear gradients. So I'm going to play gradients with these shapes, nonlinear, and this kind of waveform. So they're going to sort of flip on and off. So again, our measurement is a weighted average. And again, kx and ky are going to translate our sampling function. But now, because this nonlinear weighting is changing during the readout, the sampling function is not only going to drag from left to right, but it's also going to morph up and down. So you can see that here. So this is the same, I want to emphasize, this is the same linear gradient trajectory that's going from left to right. That apparent motion up and down is really just the smear shifting from one side, the combination rather, of the nonlinear gradients and the coils are causing that smear to shift in different directions off of the main path. And that's really interesting because it gives us some benefit from oversampling and also an additional degree of freedom, which is what we had in mind when we were using these ideas to design the FRONSAC sequence, which I'll just tell you briefly about. So you can actually add this kind of encoding to any sort of sequence, but let's say here we start with Cartesian spin warp, some trajectory through k-space, and what we do is we add a small nonlinear gradient perturbation, these little waveforms here. In this case, these two gradients cause the sampling function to rotate, and then this third one causes it to expand and contract. And at the end of the day, we end up doing a much better job of sampling those gaps in an undersampled trajectory. So for example, here's the Cartesian trajectory undersampled by factors of 4 and 8, and you can see the reconstruction is very poor. There are a lot of aliasing artifacts. But when we add these nonlinear gradient moments, we do a much better job in the reconstruction. So we've also done these in humans. You can see the undersampled 4, 6, and 8 images, and FRONSAC does a pretty good job of holding it together. And what's really neat is that because that nonlinear encoding is just a small perturbation, we're preserving a lot of the strengths of Cartesian. So, off-resonance effects, timing errors, changes in resolution, all of these are very easy to deal with because they're essentially just a Cartesian sequence with a little tweak. So before I wrap up, I just want to say, so what are the advantages of looking at nonlinear encodings in image space versus k-space? Certainly there are situations where image space can be used, but in XYZ space, every data point, every encoding involves the entire field of view. It's always encoding the entire field of view. And so you need to think about the whole experimental acquisition and how that contributes to your reconstruction. If you think of things in k-space, you can focus on the fact that each data point that you choose to sample is really just addressing a small patch of k-space. And so you can think about just how a subset of the data reconstructs a neighborhood in the k-space. And that gives us a little more ability to intuitively design these trajectories, both the path it takes and also what the morphing is doing to aid in the acquisition of k-space. So in conclusion, or summary really, I hope this helped you see that gradients are physically winding spins into Fourier basis functions. That is why our data are measurements of k-space. I should say that that is true of linear gradients, not all gradients. Nonlinear gradients are important too. Nyquist criteria are really just a way to make sure that encoding functions are unique to each location of our image. So to avoid repeats, we need that our delta k is related to the field of view, and to distinguish neighboring voxels, we need to make sure that our k max has this relationship to the voxel size. And finally, nonlinear encodings can also be understood in k-space, but instead of understanding our data as individual points in k-space, we understand we're sampling weighted averages of points in k-space. And we can take those averages and we can move them around in a trajectory with the linear moments, just like we're more familiar with, but we can also use nonlinear moment to imagine morphing those sampling functions as they move through k-space. So I just wanted to thank my colleagues at Yale that I've been teaching with over the years and provided many of the slides that you saw here and many of the ideas. So especially Dana Peters and also Todd Constable and Nadine Dispenza. She's at Siemens. And thank you.